Excellent. So welcome everyone to the ESIDA Emerging Technologies Summit. I'm Magnus Egerstedt. I am the Steve W. Chaddick School Chair in the School of Electrical and Computer Engineering at Georgia Tech, and I have the distinct pleasure of being the chair of this summit. During a normal ESIDA year, what we have done is we get together for a big meeting in the spring, and we do a lot of different activities. It's always very productive and fun and forward-looking. For obvious reasons, during the last year, we decided to kind of retool how we approach things and have smaller, more targeted events scattered throughout the year that we called our summits. And for instance, we had a really good summit in March focused around diversity and inclusion. Susan Hagnes from the University of Wisconsin was leading that one. In December, we had a summit, basically, what do we do right now as school chairs and department heads in the middle of COVID? How do we cope with this? And I think that was very, very good because it allowed us to learn from each other. But now the time has come for a summit that is much more forward-looking. We're emerging from a pandemic. We're all ready to go. And we're really thinking about what is the technical and intellectual future of electrical and computer engineering. So the purpose of this summit is really to be forward-looking. And of course, this is not going to be a complete list of the things that we should be doing as ECE department heads and school chairs, but it is, the ambition is really to think creatively and actively and forward-lookingly about who are we and what does it look like. So this is a 2-day format. We're going to go from 10 o'clock to 1 p.m. Central Time today, and from 10 o'clock to 1:40 p.m. Central Time tomorrow. So it's a compressed schedule, and I'm hoping that we will see all of you not only today, but also tomorrow. The key to, I think, a really compelling program is the organizing committee. We have an amazing team of people that have been working hard pulling this together. And the summit is organized around 4 technical and intellectual themes. One theme is data science and AI. So Diana Marculesco from UT Austin and George Papas from UPenn are chairing and leading that part. Then we have the quantum engineering side, which Dan Stansel from NC State and Dominique Dagenes from NSF have put together a really compelling program in the quantum engineering space. So that's day 1. Day 2, we have one track on 5G and the future of wireless. John Papapolimero from Michigan State and Athena Petropoulou from Rutgers are running that show. And then the last track is robotics and autonomous systems. Claire Tomlin from UC Berkeley and myself are the leads on that track. So these are the 4 intellectual major themes that we're pursuing as part of this summit. And if there's anything you enjoyed during the meeting, it's probably due to 7 out of the 8 organizers. And if there's something you didn't like, you probably should blame it on the last organizer, which happens to be the last person listed there. Having said that, I also want to thank our sponsors. We are fortunate in ESIDA to have a group of corporate sponsors that work closely with us, and without them, we would not be able to be as effective as we are. And this is also represented in the program. So I just want to thank our sponsors. I also want to thank the ESIDA staff because they have worked tirelessly to pull this off. In fact, last night, it just dawned on me that, oh, shoot, I got to whip together slides. So literally, as I was sitting down to start producing the slides that I was going to present to you today, Megan, one of the ESIDA staff members, emailed me this beautiful slide deck. So as if by magic, the slides showed up. So they have worked tirelessly putting this together, and we're really grateful for that. Having said that, here is how we are structuring the schedule. So today we have 2 keynote addresses. We have Pramod Karganigar, who is the Vice Chancellor for Research at the University of California, Irvine, and Emilio Frasoli, who is a professor at ETH in Zurich, and perhaps more importantly, a self-driving car entrepreneur extraordinaire. So they're going to talk to us about their perspectives. And then we have two tracks today. We have a data science AI track and a quantum engineering track that also involves corporate suites that are attached to these tracks. So that's really the format for today. The first hour is going to be basically panel presentations and discussions, and the second hour after the corporate suites will be more of a free-flowing discussion. Tomorrow, we're following a very similar format, but we are starting with the ESIDA award ceremony. Then we have two keynotes. We have Margaret Martinosi, who is the Assistant Director for SAIS at NSF, and Chris Malakovsky, who is the founder of NVIDIA. And then we slide into the tracks, so 5G and the future of wireless, and robotics and autonomous systems, and following the same protocol as today. I should also say a few words about logistics. I mean, we're all used to life in cyberspace and on Zoom by now, but there are lots of people registered. Close to 250 people have registered for this summit. So please exercise Zoom courtesies, like muting your mic unless you're speaking. We have a chat feature. Use that to exchange ideas. Throughout the talks, if you want to ask questions, put your questions there. We may call on you to speak up after the talks to make sure that we get a lively exchange of ideas, but utilize the chat feature primarily for questions. And then when we break out into the technical themes, so today we have data science and quantum engineering, that will be set up as breakout rooms, and you will use this one Zoom link that you're using right now to access those breakout rooms. So there's only one Zoom link that we're going to use throughout the duration, and in fact, the same Zoom link that you're going to be using also tomorrow. So the logistics should be a one-click shop, possibly a two-click, because you have to select which breakout session you want to participate in, but that's it. So with that, I think we're almost ready to get started. I do have something that I want to share with you, though, and that is Kishan Baheti. Kishan Baheti was a program manager at NSF, and he very sadly passed away this year. And the reason why I just want to honor him during the opening remarks here is that he was extraordinarily influential to electrical and computer engineering, and he was a very good friend of ESIDA, and he is someone that we owe a lot to as an organization, but also we owe a lot to as individuals and individual researchers. In fact, Kishan Baheti gave me my career award 19 years ago at the beginning of time, and he has been a personal friend of me ever since. And in fact, I know that we have George Papas on the line as well, and George worked very closely with Kishan. So George, if you have a few words you want to share with you as well.
Thank you, Magnus. My name is George Papas. I'm the department chair of the University of Pennsylvania. I just want to say a few words about Kishan. It was a big shock when we heard the news on March 9th that we lost, and as Magnus said, it's a huge loss for our community. Kishan was a leader, a mentor, and a friend. As was mentioned by Magnus, Kishan loved nurturing the community, and especially the young faculty and the young researchers in any community. All of us have been mentored by him throughout the years. We all received the NSF Career Award from him, and it has been calculated that his influence has gone to hundreds of PIs and thousands of researchers, if you include young PhD students and postdocs. He truly cared about the next generation research and generation of researchers. And he constantly had workshops at meetings about thinking about how to write your next proposal, opportunities at NSF. He nurtured the community like no other person I have seen before. But above all, I think Kishan loved building communities. And Isida was one of his homes, intellectual homes. And he brought together the control community to think about the future 20 years ago. It brought together the cyber physical systems community to think about the future of the CPS, brought together the nanotechnology community, brought together the robotics and autonomous systems community. And of course, as Magnus said, that very naturally led to bringing the ECE community together to think about what is the future of the ECE community going forward. And to some extent, the reason we are here today is because of Kishan. A few years ago, a few of us started thinking very much about what is the future narrative for the electrical and computer engineering discipline. And Kishan very much brought us under his wing and nurtured us in thinking about this. And that led to actually a community working group within ISIDA that has led to a lot of these workshops and a lot of these summits that think about the future of the discipline, how it affects its vision, its research, attracting new talent, educational reforms. And in fact, Kishan is actually funding this very workshop that we are in. So with that, I think it's appropriate for me personally to dedicate this summit to his memory and to our leader and our mentor, Kishan Baheti. Thank you, Magnus.
Thank you, George. That is extraordinarily well put. And I think that Kishan would have been really happy to see that we're taking his legacy and moving forward and really, really trying to continue to forge connections with our discipline and other disciplines, bringing people together and really envisioning what the future holds. So with that, let's get the party started. So George, you actually are introducing our first keynote speaker. So I'm going to stop sharing my screen and I'm going to let you take it from here.
So it's my pleasure to introduce our first keynote speaker, Pramod Kargonegar, who is the Vice Chancellor for Research at University of California at Irvine. Pramod got his PhD at the University of Florida under the direction of Rudolf Kalman, the Kalman of the Kalman filter, then went on to Michigan to have a glorious career, a pioneer in many fields in control, robust control, semiconductors, and devices. And then he switched to leadership side, where he became the Dean of the engineering at the University of Florida. He was also department chair at ECS, and then switched to even grander national leadership by becoming the director of ARPA-E, one of the new, the DARPA of energy, before switching to NSF and becoming the director of engineering, where he was managing a $1 billion portfolio that affects many of our departments research-wise. The reason I thought it was very appropriate for Pramod to sort of launch this summit is, going back to the discussions with Kishan, is that a few years ago, I recall at an ISIDA conference in a plenary session where Pramod kind of challenged the community to really think about a new narrative for our discipline and a new vision, and that can sort of share and make a compelling case both to policymakers in Washington or Brussels or other agencies, as well as to parents and students, and draw talent to the field. And I think it's very appropriate for Pramod to come back and tell us, how are we doing? Are we on the right track? And what else should we be thinking? So with that, I'd like to invite Pramod to tell us, share a little bit about his thoughts about the future.
Thank you, George. And thank you, Magnus, for having me here. Let me share my screen. It's an honor to be with this group. I used to be a member of what it was called EEDHA a long time ago when I was chairman of ECS at Michigan, and have enjoyed my connection to this community. And so just delighted to be here with you, sharing some thoughts. Let me begin before I sort of tell you what I'm going to talk to you about. Just want to again reiterate the huge debt that all of us owe to Kishan. Me personally, I knew him since his days at General Electric. He funded me when he was at NSF. Then we worked together when I was the head of engineering at NSF, and he's just been a lifelong friend, and we miss him dearly. So I dedicate the rest of my talk to Kishan, who was a great friend of ISIDA, a real champion of ISIDA. I can tell you that from inside at NSF. So what I want to talk to you about is 5 things. Hopefully I can get it all done quickly enough that maybe there will be a minute or 2 for questions. I think we're running a little bit behind time. So I'm going to talk to you about convergence, team science, inclusion and diversity, emerging technologies, and then just one concluding slide. Okay. So what is convergence? Convergence is on a stream of thinking that goes from unidiscipline to multidiscipline to interdiscipline to transdiscipline. And in my first 5 to 7 minutes, I'm just going to try and explain what this idea is. So just to set the stage, we all know what a discipline is. Sort of science, engineering, technology has grown, and the entire academic enterprise has grown around the idea of disciplines: mathematics, physics, chemistry, electrical engineering, which we all love. These are all disciplines. And then the next sort of stage is multidisciplines. So sort of definition is juxtaposition of 2 or more disciplines on a question or problem or topic or theme. It's juxtaposition, but individuals work separately, results typically published separately or compiled, but not synthesized. Next level of change is interdisciplinary. So interdisciplinarity means integration of information, data, methods, tools, and concepts, and or theories from 2 or more disciplines. So the key defining concept between for interdisciplinary versus multidisciplinary is you begin to have integration. So individuals still may work alone, but increasingly the research is team-based. Collaboration introduces social integration, project management, and so on and so forth. Finally, on this journey is transdiscipline. So at this point, you begin to transcend disciplinary approaches through comprehensive frameworks and paradigms. Other shift that happens is it's problem-oriented research that crosses boundaries from both academic and public and private spheres. Mutual learning, joint work, and knowledge integration become key to solving real-world problems. And finally, probably the most important part, which is not always realized, is to foster new worldviews or new domains that didn't exist prior to coming to this level of integration. That sets the stage for the concept of convergence. The concept is now about 10, 12 years old. And if you go back further, Mike Rocco was thinking about this back in 2003, 2004. And there have been a series of reports that have laid out this convergence paradigm that I'm going to talk to you about next. I've just shown pictures of 3 recent reports. I'm going to send the slides over to Magnus or George so that you can all see them. They're all hyperlinked, so you can read them at your leisure. So I'm just going to highlight a couple of things. NRC report on convergence essentially makes the case that it's a method for creating new knowledge, which is distinct from the way we have created knowledge in the past within our disciplines. So it's an approach to problem solving. It integrates knowledge, tools, and ways of thinking, comprehensive synthetic framework for tackling science and societal challenges. 2 closely related but distinct properties: convergence of expertise and formation of a web of partnerships. I had the honor and opportunity to really push the convergence idea when I was at NSF, and it's now a significant part of NSF's portfolio of research that they are funding. There's a convergence accelerator that has sort of brought this to much bigger life. But it's essentially from NSF viewpoint, what we said is, or what I said when I was there, and what NSF still says is it's two pieces: research driven by a specific and compelling problem, so need to address a specific challenge or opportunity. And it can range from deep scientific questions to pressing societal needs. It's not necessarily just societal needs. It could be a scientific question or a technological opportunity. And then second piece is deep integration across disciplines. So knowledge, theories, methods, data, research communities, languages intermingled. And it's not here, but ways of thinking that we can bring together to a problem that comes from distinct disciplines. We all think different, and if you bring people together, they will think different. There are 4 pillars to convergence: people, organization, culture, and ecosystem. In the interest of time, I'm not going to go into the details of this, but these are really, really important pieces to understand, especially the culture and ecosystem pieces. Convergence cannot happen without team science, without team research. So I want to spend just a couple of minutes talking to you about team science and team research. There is a plethora of literature on team science. In fact, UC Irvine is blessed to have some of the world's leading experts in team science. It's a new sort of field to understand how people can work together to produce new knowledge. So it's really much more about people interaction and how do you form teams. So diversity of team members, disciplinary integration, what's the right team size, how do you get goal alignment between team members, how do you create permeable boundaries within the team? Does geographic proximity play a big role? How do you deal with virtual environments, especially post Zoom? This is going to become a big topic. How do you get teams working across the world? And then task interdependence in a team. These are all become pieces of the team science. And Dan Stokels, who's a colleague at Irvine, has this beautiful diagram that covers the whole system is seen from individual team members at the center of the circle all the way to team's immediate environment. So this could be physical, spatial, social, organizational, within a university campus or between a university campus and a company and so forth. Then institutional environment, where there are multiple teams working on multiple different problems, and then much at the highest level, at sort of the national and global levels, how does it influence convergent science beyond the team and its immediate environments? And so who are the players? Funding agencies, government policies, private sector, NGOs, they all play a role in this. There is now a lot known, although not widely practiced, I must say. We know a lot about how to do this well, but most people don't know it. How do you improve team effectiveness? Through team processes, team composition, team professional development, leadership. Are we creating leaders who can do this kind of team research? Support for virtual collaboration, organizational support for team research. These are all ideas. There is enormous amount of knowledge about this. I'm going to make it really short for you. Like I said, UCI is blessed to have 4 of the world's leading experts on team science. So what we did about 2 years ago, we created something called the Team Scholarship Acceleration Lab. And we put scholarship to include humanities and social sciences. We didn't want this to be a purely STEM enterprise. We wanted to bring all those people in. So if you go to this website, there is a whole bunch of tools and techniques and really usable things that you can go and browse and use and connect with us if you're interested. Next piece I want to talk about is inclusion and diversity, which is really a big challenge for STEM and big challenge for ECE. So a central hypothesis of convergence is that diverse teams generate innovative solutions. An environment where opinions, especially dissenting opinions, are openly expressed, where diversity is valued, etc., may be vital to success. And this was in the convergence report from NRC. Here I want to kind of point out different facets to diversity. So there is the functional diversity, problem-solving approaches. And then there is demographic, cultural, and ethnic backgrounds, identity diversity. And both of these are really, really important. I mean, it's not like one can substitute for the other. And we need to be mindful that these are independent dimensions to diversity. And I do want to say that this is a challenge. I mean, this is not easy. Relationship with team performance, challenges in social integration and communication. Perspectives can mitigate and reverse these effects, but they have to be done in a respectful and inclusive manner. It can lead to greater creativity and satisfaction, but environment with diverse views and perspectives can be uncomfortable for team members. So unless you're really careful, this whole thing can fall apart and the teams can become dysfunctional. So inclusive attitudes and management strategies and leadership is absolutely critical. Okay, the final piece. So how does this all come together? in emerging technologies and innovation, which is really what you are all going to talk about. So I want to share 3 pieces on this, 3 really very interesting articles. So first is a recent paper by Bloom et al. In 2020. This actually is a 2018 paper, but it's now published in 2020. And essentially, they make the case through extensive data analysis that the amount of effort that is going in creating and producing innovation is getting bigger and bigger and bigger. And I just put 2 charts. Essentially, what is the effective number of researchers for a given level of economic growth? So essentially, you can say that the economic growth has been stagnant or flatlining or even declining by some arguments. And the number of researchers it's taking to just keep us at that level is just sort of growing enormously. And same thing, aggregate evidence on research productivity. So, and they do sector by sector analysis, including semiconductors. It's worth a read. I mean, I don't have the time to tell you about the semiconductor piece. It's and they do agriculture. They do all sorts of sectors of economy to show this phenomena that's happening. Second piece of what I personally have learned in my time about innovation is increasingly combinatorial. And I'll make it short. And again, I will share the slide so you can see the paper. Most of the patents are multidiscipline. So, so this is patent data analysis, and you can just see the divergence in the number of patents that are within a discipline versus across disciplines. So it's like 2 orders of magnitude, if not now greater than 2 orders of magnitude difference in innovations that are happening because you're cutting across fields as compared to staying within a field. So that's the second piece. Third piece is another really amazing piece of work. What it did is it looked at innovative papers, which is the currency that we all have, right? I mean, we are professors, we write papers. What are innovative papers? So they looked at the references in a paper, and they computed two metrics: the mean age of references. So like how recent are the references? You can compute the mean age and the distribution or coefficient of variation. And there is a sweet spot that occurs where the mean age is relatively small, but there is a significant dispersion. What it says is, and so the punchline of the paper, which again is a beautiful read, is high impact papers combine in a clever way recent advances with some old insight. So this clever combination is really critical. So these are the 3 pieces that I think are central to innovation in the future. So working hypothesis that I work with is that inclusive and diverse teams in the convergence research paradigm will innovate effectively to generate valuable new technologies and value to society. So what's my sort of, I implore you to think about these things. I made these slides before I saw your 4 breakouts. Okay, trust me, I did not know what Magnus was going to say. So ECE is absolutely central in several of the biggest emerging technology opportunities: AI, ML, quantum information science, wireless. I actually had 5G and beyond, which is what you had. Then I turned it to wireless because people want to think broader. Robotics and automation. And then I had these things which you don't have, but I think there will be people within your group that I want to talk about beyond Moore's law, smart grids, and some of the other big technological opportunities in front of us. But that's not the only thing. So clearly, this is where ECE is central and is going to lead. But ECE can also play a significant role in addressing societal problems, where the role of ECE could be more like a team member, a critical team member, but may not be necessarily to lead. But I think that's okay. We cannot just ignore that piece because that is so central to the future. So things like energy and climate, future of work, health and aging, resilient infrastructure, cybersecurity. So it seems to me that ECE can play in both of these domains, and the ECEDA group is the key leadership group to lead the innovation ecosystem to make a big positive impact. So on your campuses, off your campuses, I think you guys and women can do great work, just great work, leveraging all that we have learned about convergence, team science, inclusion, diversity, and make a big impact. So that's sort of my challenge to you. I would welcome any questions, comments, ideas, and I'll stop there, George. Thank you very much.
Thank you very much, Pramod. Thank you. Thank you. If you have any questions, please raise your hand in the Zoom and I will call you until Magnus kicks us out. While we wait for somebody to raise their hand, I would like to ask a question, Pramod, which is, how should we be thinking educationally as ECE leaders to sort of support the convergence paradigm early on in the thinking of students and young innovators?
Oh, there are so many things I can say about that, George. First is, of course, in our teaching curriculum, we do a lot of team projects, right? But having teams that are diverse, having teams from across the campus, teams don't have to be ECE teams. I mean, making an effort to expose them to working with social science, students from social sciences or from other fields, I think would be an absolutely critical thing to do. Second, we know that inclusion and diversity are a big problem for us. And so, but we also know that women and underrepresented minorities are attracted to the societal challenges like energy and climate. They see this as their problem. So we can, we as ECEDA leaders can work on that as well. And I think we should really be making this a central piece of our curriculum, both in the classroom as well as outside the classroom.
Thank you. Assad, you'd like to go with your question? Please introduce yourself, your institution, and then go. Yeah.
Sure. My name is Assad Zemi. I'm the chair of electrical and computer engineering at the University of Wisconsin-Platteville. And my question is, what is the relationship between the convergence that you were talking about and the systems thinking and systems approach? Because it looks like there are some overlaps between the two approaches there.
I think I'm just glad you asked that question, because convergence requires systems thinking, and this places ECE fields in the middle of making a contribution, because we think in systems. And so systems is a necessary condition, but it's not sufficient. So I think having the systems background systems. The other thing I will say, which I think we should all recognize, is many communities claim to own systems. So ECE is not the only community that says we own systems. I mean, there are a lot of other fields that say, in fact, I gave a talk once and I found that systems is one of the 100 most used words in the English language. Okay, one of the 100, just think about that for a second. Okay, one of the 100 most used words in English language, systems is one. Every field has systems in it. So having said that, I think ECE and the training that we go through in terms of building systems is, I think, really an important piece. And it's a necessary condition for convergence.
So thank you so much. I'm gonna exercise chair's privilege here. But Pramod, thank you so much. That was a great talk. And was this in person, you would hear a resounding round of applause. You have to do with the sad sound of a single hand clapping in cyberspace. But thank you so much. This was excellent.
Thank you for having me.
Absolutely. So with that, let's move on to the next keynote, and Professor Claire Tomlin is going to be conducting the festivities. So Claire.
Yeah, thanks, Magnus. And thanks for inviting me to introduce Emilio. I am a professor of EECS at UC Berkeley, and in about 2 weeks, I'll be the new chair of the Department of EECS at Berkeley. So probably joining this meeting more often. So it's a pleasure to introduce Emilio. Emilio Frazzoli is a professor of dynamic systems and control at ETH Zurich in Switzerland, and he has a storied career in both academia and industry. So after receiving his PhD from MIT AeroAstro in 2001, he spent about 5 years as an assistant professor, first at UIUC Aerospace Engineering, then UCLA Mechanical and Aerospace Engineering, before he returned to MIT AeroAstro as an associate and then a full professor. And then he became the director of transportation at MIT. And in 2013, Emilio co-founded and he became the CTO of Newtonomy, which is a company that made software to build self-driving cars and autonomous mobile robots. And it also launched a robo-taxi in both Singapore and Boston. Newtonomy was subsequently purchased by Delphi Automotive, which is now Aptiv, or part of the Motional autonomous driving joint venture between Aptiv and Hyundai Motor Group. Until this year, Emilio was the chief scientist of autonomous mobility at Aptiv Motional. And in 2016, Emilio joined ETH Zurich. So Emilio's research focuses primarily on autonomous vehicles, mobile robots, transportation systems, and in particular on smart urban mobility. His academic work is inspirational and highly cited. Two examples include a paper from his PhD thesis on real-time motion planning for agile autonomous vehicles, and also a paper with one of his PhD students who's now a professor at MIT called Sampling-Based Algorithms for Optimal Motion Planning. Emilio is a recipient of the NSF Career Award, the IEEE George Axelby Award, and the IEEE Kiyo Tomiyasu Award in 2017. Emilio.
Thank you, Claire. I must say, thank you for the introduction. It's amazing work reconstructing everything. I should have recorded you and use it for my own bias. Thank you very much. So, pleasure to be here. Let me see if I can share my screen. Okay. Okay. Can you see the slides?
Yep.
Okay, perfect. Okay, so my talk is, as you can imagine, I've been working a lot recently on self-driving cars or autonomous vehicles, and what I would like to do today is talk a little bit about what I think are really the fundamental challenges for self-driving cars. This may not be what you expect, but hopefully I can convince you that those are the real problems. Okay, so I mean, self-driving cars have been popular for many years. I will not go through why we are working on those things and what are the main benefits, but people always mention better access to mobility, better use of our time if we don't have to be to pay attention while we drive, or we can do other things while we are in the car. But with all the potential benefits that you can imagine, there is a necessary condition for acceptance of all this technology, that is a belief that this technology is safe enough to be operated on the road. Okay, so really, in order to enable all these other benefits, we really had to make sure that the cars are safe enough. But what does it mean to be safe enough? Just not to hit people or not to be at fault in accidents? Well, actually, that may not be sufficient, because in fact, what is happening today, if, for example, if you look at like a Waymo's cars and other cars that are operated by many of these companies, is that, yeah, it's true, they get involved maybe in very few accidents at fault, but they get involved in accidents, period, which they're not at fault, at a rate that is much higher than human-driven cars. And this is something that these companies don't really tend to emphasize, and people are not necessarily aware of. And essentially what happens is that these self-driving cars are kind of behaving some kind of like odd ways, and they brake in the middle of the road for no apparent reasons, and then people rear-end them, hit them, and they don't know how to deal with them. So, one way you're looking at this is the following. So everybody, every single person working on autonomous cars always say that safety is their main guiding principle. However, there is no clear specification of what safety means. Okay, and I think that we are educators, right? So, and in engineering programs, typically what you do is when you talk about like a big project, like a big system design, is the very first thing that you do is set up what are the requirements, right? And then you go through your design process. The big problem here is that we don't have those requirements. Okay, so if you look at the rules of the road are written by humans for human consumptions, are often based on legacy. In fact, you may not be aware of the fact that a lot of our rules of the road actually originate from Roman time laws, or even before. There were rules that are actually designed to govern the way that animals were controlled, like sheep and goats and horses and cows and things like that. So then this system of rules is actually incomplete, not precise, at times contradictory, right? And it's open to interpretation. And you may not be aware of the fact that it's actually legal to break the law in order to ensure safety. So, and in fact, if you don't break the law, you may actually be breaking it at a more higher level because you are endangering you're putting someone in danger. So what needs to be done is that AVs, the autonomous vehicles, and in fact, the companies must be able to demonstrate the fact that they internalize what is called a reasonable level of care towards other actors on the road that is comparable to that of human people. In fact, in a lot of the regulations and the law and cases and in the US, there is this notion of a reasonable person, what a reasonable person would do. Now, what is a reasonable person, or who is a reasonable person? I have no idea. You show me, right? But that is a concept that is actually very common in the legal practice. So typically what people do at this point is start throwing things like ethics, right? So ethics is an approach to deciding how to act, when other, criteria given by the hard sciences are not sufficient. The problem with this is that as soon as you start talking about ethics, then somebody is going to throw at you these what is called like these trolley problems. Okay, so these very high stakes kind of like problems where, okay, so now your car is driving down the road and either you hit 5 children or you need or you hit like a 2 elderly persons, or you hit like, I don't know, so or you kill all the occupants in the car, right? So you are presented with this kind of ethical, this very high stakes problem, which, yes, they are pose an ethical challenge, but for me, it's a challenge that is more useful for entertainment purposes at cocktail parties, right, the dinner parties, than for actual design of autonomous cars. In fact, what you have is a lot of other dilemmas, if you will, that happens every day. Every time you take the car, you encounter one of these. One of my favorites, especially given my experience in Singapore, driving on the streets in Singapore, is this one. When you're driving in your lane, there is somebody that is parked in your lane, and then in order to make any progress, you have to get into the in the opposite direction lane. Okay, so here you're technically violating a law, right? So because you're going into the opposite lane, but you kind of had to do it because otherwise you will be stuck, and everybody does it, right? So then there is this notion that sometimes it's okay to violate a law as long as you can do it safely, right? And these low stakes dilemmas, I can give you, a lot of examples. These are all dilemmas that occur very frequently during normal driving, okay? In fact, what I have is what is I consider like a well-posed trolley problem. So imagine the situation where you're driving down the street and then there is somebody who is jaywalking, just a pedestrian that is crossing the street, okay? He shouldn't, or she shouldn't have, right? But the fact is that this person is in front of you. Now you have 2 options, like called option A, the braking option. So unfortunately, you don't have enough room to stop. So with probability 1, you will hit the pedestrian, okay? But it's not your fault because they shouldn't have crossed the street and you tried to brake, you did your part, right? The other option is to do something else, let's call it swerve. But now if we do some emergency maneuver, some swerve, then maybe with some probability P, we hit another pedestrian, but who is just an innocent bystander. And in this case, this is definitely our fault. Okay. Now think about this. So if P is equal to 1, so we will kill the person, we will hit the person if we swerved, then definitely we hit the person who deserved it. Okay. If P were equal to 0, so that if we swerve, we don't do any damage, then we clearly will decide to swerve. Now, you can have some kind of hands-waving argument, continuity argument here, and say, well, if this is the case, then there must be some value of P, let's call it P star, at which we decide whether to swerve or not. Okay? Who sets this P star, and how do I compute it? We can make the problem even more complicated. Now, instead of knowing with certainty that there is a pedestrian in front of us, we have some noisy sensor that is telling us that we think that there is a pedestrian in front of us with some probability Q. If it comes to it, again, with probability Q, we hit a pedestrian that may or may not be there, but is not our fault. And or we swerve, and with probability P, we hit a pedestrian, and it's definitely our fault, right? And again, this is a case in which, as a function of P and Q, we can define what is the decision threshold. Okay. Now, the problem is who has the authority to set this value? Who should set these values? And unfortunately, okay, so this situation where it's hard to know where the buck stops, right? So, so there are many parties that are part of this, stakeholders, right? There are the parties in the technical sphere, the industry, academia. There is the legal sphere, there is the government, the authorities. There is the social sphere, right? So, what is the public willing to accept, right? And from my point of view is that this kind of criteria should be set by the community. Of course, you cannot get all the people together, maybe through their elected representatives or through the institutions that are created to handle these kind of things. Unfortunately, what is happening is that since the institutions and the authorities are not really stepping up, their game and coming out with these criteria, a lot of it is left to the technical sphere, and then you have the technical companies coming up with their own rules. But we know how successful that was, for example, with social networks and things like that. Right. So let's say that we do have a set of criteria for how these things should behave. Okay, so then what are the approaches to implement this these criteria? What you have is a traditional logic-based approaches, like if, then, else kind of, algorithms and criteria that are, out of favor these days, right? So now everybody's talking about learning and things like that. So because people say, well, there are too many cases, too many rules, so we have no hope of resolving that. So just learn, throw data at the problem and let the system, computers, neural networks learn what is the right behavior. From my point of view, complexity is a limit in both cases. You have computational complexity on one hand, for all the if then else kind of like statements, but then you have a sample and model complexity on the other hand, right? So what people don't realize, if you have all these many corner cases, then yes, if of course it's many cases from many options for a rule-based approach, but it's also many corner cases. You need to have sufficiently many samples, examples of good behaviors in those cases so that you can learn all of those cases. And again, so you need a lot of exposure, lots of data, really a lot of data, and also the models that are rich enough to represent those things. Then debugging, verification, validation is very hard, as we know, both in the traditional methods and in the learning-based methods. And I would say that even the maintenance and the updates and the fixing things is also very hard, right? So for example, if you see that an approach based on learning has some faults, some bugs, then how do you do, what do you do to fix it in a provable way, right? So you're not just to say, well, I need more data and hope that with more data I fix the problem, okay? So We have taken a slightly different approach, and so there is this thing is another A in AI, which I think of it as accountable intelligence. So if you think of it, how do we teach humans to drive? We don't show them what to do in every possible case, right? So we teach them the rules, okay, and we have some criteria, and we hold them accountable to those rules, okay. And in fact, if you look at the rule books, the little booklet that you study before taking your written test at the DMV or whatever authority issues your driver's license, the rules of the road are not that many, okay, and in fact are easily learned by 16-year-olds, okay. So it's about 12 classes of rules at the end of the day. Okay, so rules that says, who can drive what, when, and where, what speed, in which direction, who has the right of way, how to read signals, and where you can park and you can stop. Okay, so my point is that it's very hard to code good behaviors, very hard to learn good behaviors, but it's actually is very easy to assess good behaviors. And this is what we leverage. Okay, so essentially what we want to do is get to what I call this accountable intelligence. We want to go from the laws to specification to implementation to executed behavior and back. We want to know why the car did or did not do something. The system must be auditable and must be maintainable. So if we find a case of non-compliance, I must have a way to resolve that non-compliance in a systematic way. The approach that we've been pushing is something that it goes by the name of, we call it like a rule books, because essentially what we have is a collection of rules, and which include a natural language description, but actually is a very precise formal mathematical description, including scope and definitions, and a constraint statement in some, like a formal language of your choice. With a violation metric, so if I violate this thing, how bad it is, right? And how much worse it gets the farther I get away from my constraint. And then we have this, the rule book is a collection of rules, which is hierarchical in the sense that some rules, I like to say this thing, that all laws are equal, but some laws are more equal than others. So some rules are actually more important than others. And then what you want to do is have not only a collection of rules, but a hierarchical collection of rules. And actually what you have is what is called a pre-order, which is a partial pre-order, in fact. And then what in implementation you want to convert to a total ordering. But anyway, so this is more on the technical side. How do we use that? If you know my past, probably you can get a sense of this, of my approach to these things, is that the way to get good ideas is to get lots of ideas and throw the bad ones away. So we do this by pairing a unbridled creativity with a good taste in selection. And essentially, for example, for planning, what we do is we have ways that to generate a whole lot of different behaviors, right? So what if I did this? What if I did this? What if I did this other thing, right? So try to express a whole lot of different behaviors, cover the space of behaviors in some efficient way, and then have a way to efficiently check how each one of those behaviors does according to my rules, and choose the one that actually, if I, that satisfies all the rules if I can, or if I had to violate some rules, find the ones that violate the lowest priority rules as possible, okay? And essentially this is how we handle, the whole system. So we have perception, right? And, these are the traditional pieces, right? And we use all technologies that are available today. So we use deep networks, different sensors, different representations. You want to have, people always say, do you need video cameras? Are video cameras sufficient? Do you need lidars? Do you use other things? For me, the more diversity, the better, even in this case, right? So, it's important to have, for redundancy and in sensing as well, to have different algorithmic approaches, but also different physical sensors. Planning, again, I'm not advocating any particular approach. In fact, what I'm advocating is a collection of approaches, because what I want to do is generate efficiently a collection of sufficiently diverse candidate behaviors. And then the key in all of this is this arbitration layer, where we evaluate candidate behaviors according to these rules of the road and choose the one that minimize the violation of these rules. Typically, these have a formal structure. For example, I know that at a certain intersection, I have to yield the right of way, but there is no formal definition of what right of way means. So where do we get that? And this is for me as a candidate out of, for really like a data-driven statistical, kind of argument in which what you say, well, what we observe is that people tend to get upset when other people cut across, their path in these conditions. So essentially what I'm saying is that for me, these rules have a formal structure that is kind of predefined because, that's something that we kind of know. The parameters in these rules are often collected based on data-driven experiments or the collection or procedures. In fact, what we use is, I was talking about this concept of a reasonable person. What we do is what we call a reasonable crowd. So essentially we look at, collect, vast amount of data and see how people react, based on that data. Okay, so let me conclude. What I think is the real Achilles heel for autonomous vehicles today is that we don't really know precisely how vehicles should behave, and that applies both to human-driven and robotic vehicles. So what we really need to do is find a rigorous way that AVs internalize a reasonable level of care for other actors on the road. So what we need to do is develop a consensus in the community for what is a sound theory of behavior for autonomous vehicles, so for robots, autonomous robots in general. There's a combination, there's room for a combination of formal first principle and statistical learning-based approaches in this area. Now, something that is important is that behaviors are actually assessed post facto, okay? So if you hit a person, you cannot say, oh, I didn't see them, right? So the behavior is assessed post facto on realized space-time trajectories independently of what you thought. On the other hand, you must make decisions based on what you have observed and what you think. So how do you reconcile these things? And for me, compliance with the rules, this accountability really drives the requirement for the system design from planning, control, but also perception. Then something I didn't touch upon in this presentation is that precise and ethically sound specifications are needed not only at the level of the single car, they're also needed at the fleet level. So for example, it's important that if you want to provide mobility, we want to do it in a socially equitable way. We want to be fair to all segments of society. We want to provide access to mobility to everybody, and because this is really something that has the potential to shape our cities, lives in our cities, and that's something that really need to be done in a socially conscious way. So I will stop here, limitation of time, I will be conscious of time, and thank you for your attention. I'll be happy to take any questions if you have any. Thank you.
Thank you, Emilio, for that great talk. I think we may have 1 or 2 minutes for questions as we started a little bit late. So as people are thinking of their questions, and I see they're starting to come in on the chat, I'd like to just ask a first question, which is about this notion of responsibility and the encoding of that hierarchy. So you talked about the kind of legal and social circles and the technical circles, but if companies don't have that, or companies, technology, universities don't have that sort of push from legal and social as much as they do from technical, then how do you ensure that that hierarchy is correct? That the way you sort of move through that hierarchy when you as the autonomous car are deciding on what decisions, like how to, what's the least worst way to break the rules? How do you make sure that's socially responsible?
Yeah, so just give me 1 second. So so I was trying to get to this slide. So, Claire, this is the main thing. This has been for me the main thing, since I started working in this area. So essentially the idea is that I don't want I don't want it to be the one setting those rules. I think is the job for somebody else. As I said during my presentation, I think is the community that needs to come up with these rules. Right? Now, how do we do that? Now, I've been trying to provide the technical means, working with the government, with the authorities, with the public. Very first thing, I think that, for us, it's always been very important to do public pilots, not only as a demo, but also to on one hand, to learn how the public will interact with this technology, but also show the public what the benefit to them this will be, okay? And also show the public what the limitations of this technology are, right? Because there is this danger that everything looks like magic, right? And then people believe that these cars will do, will take accident to zero, forgetting that, these cars will not, no technology will eliminate inertia, right? Or at least, no technology is known to man at this point. We have also been always working with the authorities. So in particular, we'll be working very closely with the Singaporean government. And in Singapore, things are a little bit easier. There are fewer levels of hierarchy to approach, and there are you don't have to deal with like 50 states, just with this one set of, one ministry, right? And in fact, we have given substantial input to their technical reference 68, that is actually essentially the predecessor to what will be their regulations for autonomous vehicles. So we've been working very closely with them to give input, what should be the rules, how do you do all the testing, the certification of autonomous vehicles. So I think it's important that they do it, but we need to help them do it. Also, something that is important is we have seen with Uber, right, and Lyft and all this ride-sharing revolution is that has happened very quickly, and in fact has taken the government and the authorities in many cases by surprise. And they've really been struggling with how do you handle all these things. Now, with autonomous vehicles, that is something that is not happening overnight. It is very clear, right? So I think it will be years, right, before these vehicles will be widespread and driving in all our cities. So I think that is really this opportunity for the authorities worldwide to really think hard about what they want out of these systems, so that they can shape the regulations and the incentives and the constraints and the criteria for the industry to offer the technology that will actually make our lives better rather than the other way around. So I really wish that government and authorities worldwide will use this time window to really come up with comprehensive regulations for this technology. Other things that we are doing is, I don't know.
No, I was gonna jump in and keep this ship on track. So Emilio, thank you so much again. A loud round of applause from cyberspace. It was great to see you, and we have officially changed the name of this summit from the Emerging Technology Summit to the Unbridled Creativity and Good Taste Summit. So really excited about that. Thank you so much. So we are now moving on to the two parallel